Hello everyone, let us start off with the chapter on scalar and vector. On this side are all the examples of scalar, this side all the examples on vector. For vector, aside from just a numerical value, there's also a directional component. So for example, for the case of just a mass of 5 kg, correspondingly its weight of the 5 kg could be 5 multiplied by the acceleration due to gravity, that will be 5g. But more importantly, the weight is all directed downwards. Volume 10 cm3, there's no directional component. When you deal with any forces, we will always say 5 Newton, and we will be looking at the direction, whether is it moving forward, backward, or downward. The other two examples are actually distance and speed. Both these are scalars, there's no directional component. Displacement and velocity would have a directional component. And finally, as far as for acceleration is concerned, it is the rate of change of velocity, and therefore acceleration will be affected by directions, while time is not. With that, let me give you an illustration on how we calculate distance and speed, and how that could be different for the same moving object when we calculate displacement and velocity. So say for example, we actually have a car that moves from point A to point B in 1 second, traveling 3 meters. Then it turns right to move 4 meters, again using 1 second. And you will find that in this case, the distance traveled will be 3 plus 4, should be 7 meters. However, in terms of displacement, it will be 5 meters. Because as far as for displacement is concerned, it is just looking at where the start state of the car is and where the end state is, and obviously there's a directional component, theta. All right, and given that theta is here, we could say that displacement is 5 meters, and basically subtended, and the direction is actually has an angle theta, which is tangent theta is 3/4. So therefore, theta is tangent inverse 3/4. Okay. So you can see that the displacement is a vector component. Therefore, there's a magnitude, and we also have a direction. All right. Next, we'll look at now the speed. As far as the speed calculation is concerned, again, it will be 3 plus 4, which is the distance traveled, divided by 2 seconds, and that will give us 3.5 meters per second. In the same way, like displacement, velocity will be just looking at 5 meters, which is the magnitude, and that will be 2.5 meters per second. And similarly, tangent theta, the direction will be 3/4, implying theta is tangent plus 3/4. So this is a quick example to contrast the difference between scalars and vectors. Let's take a look at another example. Say we have a moving object that travels at constant speed along a semicircular path, and basically it travels from A to B, all right, covering half the circumference of the circle, all right, of the circular path. You could see that in this case, in terms of the distance traveled, it will be actually the half the circumference of a circle. So that will be half times pi over d, and that will be actually that will be just pi meter, which is actually 3.14 meter. Okay. Then as far as for displacement is concerned, displacement in this case will just be 2 meters, but more importantly, we can say the direction is in this direction. So a displacement has a direction component. And as far as for the speed, which they mentioned is 1 meter per second, all right, we could now work out the time it takes. So the time it takes for us to get to A to C would actually be the distance, which is actually 3.14, divided by the speed, which is 1 meter per second. That would be 3.14. seconds. And hence, because of this, the velocity will therefore now be equal to 2 meters divided by 3.14 seconds. Okay, that we could work out. But more importantly, we also want to emphasize that the velocity has a directional component, which in this case is actually horizontal. Okay, let's now use the same two examples to illustrate how we can calculate resultant velocity as well as acceleration. We take a look at this one below first. It travels down by 3 meters per second, and then it moves towards this side by another 4 meters per second. So in terms of the vector diagram, it will be u going this way, which is v. So the resultant would actually be equal to u plus v. You could also represent it with this. Okay, so in the case, this will be the resultant. In the same way, if you were to take a look at this and we break it down into many little components, obviously it will start off with adding up basically all the various components of the small little vectors that when the speed actually has changed. So in sum up, it will actually be this will be the resultant, which is actually the summation of all the speed. All right, all the speed that string up. So in summary, this is the resultant velocity for the object in the semicircular motion, and well, this is the resultant velocity. All right. Let's take a look at acceleration. So as far as acceleration is concerned, acceleration actually has got the v minus u. These two is actually both vectors component, while your time, your change in time is actually a scalar. So the key thing for us will be to look at change in v over time. So the change in v is actually the scalar, the vectors component. So the change in v is actually the vector component that will be interested. So change in v in this case would actually be v minus u. All right. And in terms of vector diagram, this will be the case. So with that, let's take a look at the this example. So you can see that we could. So take a look at let's take a look at this example. So you can see that this is your u, and this is the v. Okay. So given that change in v plus u will equal to this, so this plus this, so this is actually the change in v, because u plus change in v will give you actually the velocity component. So in this case, for this motion, the acceleration, the direction of the acceleration is the same as change in v. All right. So a will now be change in v over t, like we mentioned. But more importantly, we know that that's the direction of the acceleration. Okay. Let us now apply this for this example. So u is going up while v is going down. Hence, in this case, the change in v will be in this direction. Okay. So with that understanding of the vector diagram, we will now calculate the acceleration for this example. We know that it takes the moving object from A to go to C is 3.14 seconds, because originally the given diameter was 2 meters. Okay. So with that, if you want to work out the magnitude, all right, of the acceleration, okay, the change in v itself in terms of magnitude will be 2 meters per second, and the time will be 3.14 seconds. And with that, you will get actually about 0.6 meters per second squared. And obviously the direction of the acceleration is actually in this direction, is downwards.